feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we continue our work with rational expressions. Today we are going to put the final touches on simplifying and working with arithmetic on rational functions, rational expressions, and it's often the most complex method as we start to deal with what we call complex fractions. Complex fractions, or often known as compound fractions, are essentially fractions within fractions. So if you take a look at problem number 4, we can see some fractions in the numerator and fractions in the denominator. We see some addition and subtraction in the numerator and denominator. Essentially, these problems incorporate everything that we've done up to this point. Now, there's many different ways to go about solving these complex fractions. One of the processes would be to simplify the numerator and the denominator through addition and subtraction, and then to multiply by the reciprocal of the denominator, turn it into a multiplication problem and simplify there. I'm going to try to show you a kind of a shortcut to simplifying these fractions in a few quick steps. So step number 1 in this process would be to create a common denominator for all of the fractions within the complex fractions. So if we take a look at 4a, we see 4 fractions there. So step number 1 is to make sure all of them have the same denominator. And if I take a look at the denominators, I have 3m, I have 2, I have 4m, and I have 3m squared. So first I'm going to take a look at the integers. So for the integers 3, 2, and 4, the least common multiple of those would be the number 12. So I can get 3, 2, and 4 each to eventually be an integer of 12 through multiplication. If I take a look at the variables, I have an m, and an m squared. So the least common multiple of m, and m squared would be m squared. So what I need is I need for each of these fractions to have the denominator 12m, supposed to be a squared there, 12m squared. So similar to adding and subtracting, when we've done addition and subtraction, I'm going to multiply into each of the fractions in order to create that common denominator. So let's start with the top fraction on the left. This top fraction on the left, to get the integer 3 to be the integer 12, I have to multiply by 4. To get m to be m squared, I have to multiply by m. And if I multiply the numerator by 4m, or the denominator by 4m, I need to multiply the numerator by 4m as well. So that fraction now is going to become, I'm going to write an equivalent expression, is going to become 8m over 12m squared. This is just part of the numerator of my complex fraction. Now, if I look at the other part of the numerator, there's a subtraction there, a subtraction of 3/2. So I need that denominator, which is currently 2, to be 12m squared. So I'm going to multiply by 6m. And if I multiply m squared, and if I multiply the denominator by 6m squared, I need to multiply the numerator by 6m squared. So that's going to turn the second fraction in the numerator to 18m squared over 12m squared. Now, I could combine those two fractions, but I'm going to leave them as they are for right now. If I take a look at the denominator of this complex fraction, I'm going to do the same thing. So the fraction on the left, the first fraction there, needs to be multiplied by 3m over 3m. And so this is going to give me 9m over 12m squared. And then the fraction on the right needs to be just multiplied by 4. It's already has the m squared value, so it's going to multiply by 4 over 4. So this would be 4 over 12m squared. So I'm keeping all of my operations the same here. The subtractions have not changed. I haven't moved my fractions around in the numerator and the denominator. All that I've done is create a common denominator. Now, what happens here? As we create the common denominator, if I have this expression, these denominators can be essentially removed or multiplied out to become 1. So essentially the next step is to get rid of the denominators. And let me show you why this works. So if I had, let's say I have a over x plus b over x. And all of that is over c over x minus, let's just say plus d over x. If I wanted to simplify this, the numerator would become a plus b over x, and the denominator would become c plus d over x. Using our rules of division, we can also write this as a plus b over x times x over c plus d. So multiplying by the reciprocal of the denominator here, c plus d over x. The x's would then cancel out, which would leave us a plus b over c plus d. This is equivalent to, from that complex fraction with all the denominators the same, just eliminating the denominators. That would be a plus b in the numerator over c plus d in the denominator. So we can essentially take this step here as a shortcut to working through simplifying the numerator and simplifying the denominator, and then multiplying by the reciprocal. So what I could do at this point is essentially, again, eliminate the denominators. And so what that's going to leave me with now is 8m minus 18m squared. Let's go ahead and flip that around. Let's put that more in standard form. That's more common. So negative 18m squared plus 8m. You don't have to flip that around, but that's just a kind of standard way to write it. And then 9m minus 4 in the denominator. Then if we can, the last step would be to simplify the remaining expression. So here I might take a look at factoring the numerator. And yes, I could factor the numerator, but I could not factor the denominator. And in this instance, if I did factor the numerator, actually, I take that back. Let's go ahead and factor the numerator. The numerator does have a GCF, and this GCF could be 2m. Let's make it a negative 2m to make my leading coefficient positive. So I'm going to factor out a negative 2m, which would give me 9m minus 4 over 9m minus 4. And now, yes, this one can be simplified. We see a common factor in the numerator and a common factor in the denominator, which can divide to give you a result of just negative 2. Sorry, I forgot my m there when factoring this. I factored out a negative 2m, not just a negative 2. So sorry, when we factored out that GCF was a negative 2m. So my final answer should be negative 2m. So that complex fraction that looked really complicated when we originally saw it simplifies all the way down to negative 2n. So we can get to this by creating a common denominator for all fractions within the complex fraction, then eliminating those denominators, and then simplifying the remaining expression. Let's take a look at another example. So in B, what we may notice is that two of these terms, one in the numerator, one in the denominator, are not written as fractions. So technically those fractions would be, or those denominators would be 1. So then our LCD in this case would just be a combination of the factors of the denominators 1 and p minus 2. So we want each of the denominators to be p minus 2. So really the only thing that we have to do here is we have to multiply the first term in the numerator by p minus 2 over p minus 2. And then also the first term in the denominator by p minus 2 over p minus 2. So I'm going to go ahead and distribute as we come through there in the numerator. So p times p would be p squared minus 2p over p minus 2, and this is the first fraction in the numerator. The second fraction in the numerator did not get changed, 1 over p minus 2. All of this is over the denominator of this complex fraction, which again I'm taking 1 and giving it the common denominator of p minus 2, or multiplying 1 by p minus 2 over p minus 2. The second term there, 1 over p minus 2, does not need to be altered. Now again, we may notice that we have common denominators for each one of these. So if that is the case, as I showed you kind of algebraically the proof of how it works, we can eliminate all of the p minus 2's in this case. And so that leaves us with p squared minus 2p plus 1 over p minus 2 plus 1, which would be p minus 1. Now I'm going to take a look at this and try to simplify if I can, and I may notice the numerator can be simplified into p minus 1 squared. It is a perfect square, so p minus 1 times p minus 1, or p minus 1 squared, and in which case then I can simplify by dividing out one of the p minus 2 factors in the numerator with the, p minus 1 factors in the numerator with a p minus 1 factor in the denominator, and my result would be p minus 1. So again, the process here is to first find a common denominator for each of the fractions within the complex fractions. So the ones in the numerator and the ones in the denominator, we want a common denominator amongst those. Then we can eliminate that denominator, combine and simplify the remaining expression. So it takes a bunch of fractions within fractions to create a single fraction, which we know how to simplify. So this is not the only way to deal with compound or complex fractions, but this is a method that gives you probably the quickest result. This looks like a good place to stop. So as we reconvene in class, we'll take a look at a few more examples and then give you guys the opportunity to practice. As always, thank you guys for tuning in, and I'll see you soon.